Worksheet 6b, also elastic torsion. The shaft shown below. So there are two materials. The first one is 2014T6 aluminum from point A to B, and then stainless steel from B to D. The aluminum section is hollow, as shown in there, and has the inner radius of 2 inches, and the outer radius is 3 inches. Determine the magnitude and location of the maximum torsional shear stress, the magnitude and location of the minimum torsional shear stress, and the angle of twist of the free end with respect to the fixed end. So it A with respect to D. So with that, the process is exactly the similar to worksheet 6A. For that reason, I want you to practice this problem before you even watch, review the solution or watch these videos to check with what level of your understanding so far before we continue. So let's do this one. As you can see in solving mechanics of material problems, basically we first find out the external forces, external reaction, then internal forces, and then draw diagram, find out stress, deflection, deformation, etc. So with that process, its own way, just start with the external forces. External forces or reactions, all of that, it will be the same in here. So with that, we draw the diagram, and for the whole shaft, so we have here, we have there, and we have the inner circle, and the inner circle have hollow section, and then our circle here, we have that, and we isolate that all of its surrounding, in this case the fixed support at D, and with that we can have the dimensions and also the load applied. So here at point A we have 10 pipe inch kips, 10 pipe inch kip, and then at point C, and for that 10 pipe, if we follow the right hand rule, if you put your right hand up, your thumb point to the positive x-axis, and you can see your other four fingers move opposite to the 10 pi inch kips at A, so that's why that is a negative moment or negative portion. So at C we have the opposite, so of the torsion at A, so that should be positive, and it will be 22 pipe inch kips. And then at the reaction at D, we have some TD there, and what I showed there is basically a negative based on the right hand rule. So we can put A, we have B there, we have C, and we have D. We can put the dimensions in there, but for if we only take moment along about the longitudinal axis X and assume right hand rule is positive, then we have 0 for equilibrium. So we have negative 10 pi plus 22 pi negative TD based on our right hand rule. So we have TD equal to 12, 5, and inch keeps. And in this case, as you can see, the right hand rules, TD is negative, so right hand rule, we have TD equal to negative 12, 5 inch keep. So that is the external forces. Do the same for internal forces. And we have three portions: AB, BC, and CD. AB, BC, and CD. So let's do the internal forces. So cut somewhere between A and B. So let's cut from left to right. So we have from A to B, we have that, and we cut this portion and there, and in, and they have a hollow, so we can have that hollow there, and it continue. We cut somewhere between that, so it will be there. So from that, you can have this is A and this is B. We cut somewhere between A and B to find out the internal force, and we assume that TAB with that case is positive TAB, and we have the 10 pi inch keeps at A. So from that we can take moment about X, and also assume counterclockwise positive equals 0. So you can have negative 10 pi plus TAB. So from that we have TAB, the torsion, internal torsion between A and B is 10 pi inch cube. And it's positive, so you have good positive based on the right hand rule as well. And as you can see, BC, between A and C, there is no torsion. So the internal torsion between BC should be equal to TAB. So from that we can also have for GC4 portion AB, and then we also have BC, it should be the same with AB. So we have TBC should have TAB, and that equal to plus 10 pi inch cubes. We got no load apply at B or somewhere between B and C. That we need to cut again to do that, but it should be the same with between AB for the torsion. And then CD, you have a 20 pi inch cube at C, so it have a change. So we can consider member CD, sorry, the segment CD, and we do exactly the same with our drawing there. Cut the hollow that go through B. So we have X, and we have this torsion at A, this is external 10 pi, and then at C we have 22 pi, and at a cut between C and D we have that is TCD, and of course between the cut, so it continue the D, it will be there. So we have A, B, C, and D there. So from that we can take moment about the x and assume positive, follow right hand rules along the x-axis. So we have equal to 0 and it equal to negative 10 plus 22 negative TCD. So from that we have TCD equal to 12 kip inch kips, 12 inch kip. And as you can see, 12 inch kips by on the right hand rule, the TCD opposite of the positive. So that you can see from that we have right hand rules. We have TCD equal to negative 12 inch kip, negative 12 inch kip. So similar to problem 6a, we are going ahead to draw the diagram, the internal shear stress diagram or torque diagram. So even the problem don't ask explicitly like it does in 6a, but go ahead to draw it so that we can see where should be the maximum torque, where should be the maximum shear stress located due to the torque applied on the shaft. So from that one we will have the with our assume x axis. So we have the x. Now we go to the left here based on our assume positive x. So we will have AB 4 feet, BC 2 feet, and CD 5 feet. So we can have A, B4, C 2, and D, CD 3. And now we can go ahead to draw the internal force. AB and BC the same, 10 kips positive. So go ahead to do with that one here. So that one is positive and this is negative. And that be the internal torsion T, and with the unit inch kips. So the AB, BC the same, positive 10 pi. So we have that is AB, BC 10 pi. That is 10 pi. And then CD, negative 12 inch kip. So going down 12. Go back there. And this is 12 pipe, negative 12 pipe. So that's what we have for the diagram. We can go ahead to put the distance. This is 4 feet, 2 feet, and this is 3 feet. And now the question asks, go back to the magnitude and location of the maximum torsional shear stress. So they have shear stress. So let's find out the stress for each. And here we only take care the stress on the surface of the shaft. Otherwise, the minimum in the center always 0 for the torsional shear stress, as you know. So find out for each AB. For AB, if you recall the equation here, the tau due to torsional shear stress due to the torque is equal to T rho over J, and rho tau maximum when rho equal to C, which is the radius of the member. So from that we can have here AB for tau AB. Tau AB equal to between AB equal T C over J. And in that case, if you want to elaborate, that is TAB. C over J. So we have that equal to between AB with 10 5. The outer radius is 3 inches, and AB is a hollow, so we apply the J for the hollow is 5 over 4. The external power 4 CI power 4 minus C inner 2 power 4. That's what they give us for the dimension of the radius. Inner radius 2 inches, entire sub radius is 3 inches. So from that we can get that one is so from that we get tau AB equal to 0.923 KSI. And then the same for BC. So we can have tau BC equal to same TBC over C times C divided by J. So C divided by J. So we have that still 10 pi, still 3. However, BC is a solid. So the J are not the same. Pi over 4, 3 power 4. So from that one, we got this one is 0.741 KSI. 0.741. And then similar we do for CD. Then we have tau CD equal to TCD. C at CD divided by J. And as you can see, if you want, you have JAB, JBC, and JCD. So from here, you can plug in at CD, the torsion is 12 pi, and we only get the magnitude here. And then 3 over also the solid, so it will be pi over 4, 3 power 4, and from that we get is 0.889 KSI. So from that we can see what is the max and min compared to all of those. So as you can see, bottom line now, the tau max, where is tau AB, right? So it will be 0.923 at between A and B and on the outermost fiber, okay? Somewhere between A and B. And then tau mean between those three components we have is 0.741 KSI. At A to B, and KSI at BC, and from that we can have our answer. And now observe, in the first problem, worksheet A, worksheet 6A, that you can see here, the maximum torsion is occur at BC, and also the torque at BC, the 6 foot kip. So the torque max in the torque between B and C, because all the along the cross section all is solid for worksheet 6A. See that? So with the maximum torque location also the maximum shear stress. However, for the problem 6b, if you observe here, because the AB have a hollow, so the J is smaller and make the shear stress can be bigger. So even between AB, you see that only the torque is 10 pi compared to CD 12 pi, but the maximum shear it occurs at AB, not at CD, because the geometry of the cross-sectional areas are not the same. One have hollow, CD is solid. So keep that in mind. It not always the maximum shear stress occur at the maximum torque. So keep that. And then now the last thing we do is number C, the angle of twist of the free end with respect to the fixed end. So with that, we can go ahead to find out the angle of twist. And this portion is exactly the same as we did in angle of twist. The same in 6a. Now, what type of material we have? We have either AB, that either 2014 T6 aluminum, and then BD is stainless steel. So we need to find out the modulus of rigidity before we apply the angle of twist. Because if you recall, the equation for angle of twist is TL over GJ based on our note. So we need to find out G, modulus of elasticity. Where we are going to find that out? Do you recall that? Go to appendix what? Appendix B. Appendix B. So, and you can see stainless steel there. Gold roll anneal. Modulus of rigidity the same. 10.8 10 power 6 psi. Okay, and then the aluminum 2014 T6, aluminum 2014 T6 in appendix B, we have the modulus of rigidity is 3.9, and also based on the column here, also 10 power 6 psi. So with that, go back to our problem here. We have from appendix B, from appendix B. So we not always the problem give you. You need to looking for the information from appendix, from all what is given to you. So we have G of aluminum equal to 3.9 10 power 6 psi, or we can say 10 power 3 ksi. And then the G, the modulus of rigidity for stainless steel SS equal to 10 power 8 10 power 6 psi or 10 power 3 ksi, because we do the kips in here, so that's why we change the unit now. So similar to the angle of twist for the worksheet 6a, so we have phi5 angle of twist of A free end with respect to the fixed end. D, in this case it's sum of all equal to sum of all the angle of twist, right, of all the phi I. So from that we can have 5 of A with respect to B plus 5 of B with respect to C and 5 of C with respect to D. So as you can see in that order, you cannot A to D and you jump AB and then CB and DC, etc. So it have to AB, BC, CD have in that left to right or right to left. Right to left, something we did in worksheet 6a. Go back to review. And as I showed you earlier, the 5 equation of 5 is LT GJ, right? So LT over GJ. So it's on the T I Li over GI JI for each portion basically. And this is 3, so make it like look like a good math, but you just apply for 3 segment of the shaft here, 5 AD. The angle of twist in this case for AB, as you can see, it will be equal to torsion at AB, so 10 pi based on the thought diagram. And it for length, AB 4 feet, BC 2 feet, and CD 3 feet. So we just convert that into inch 4, so it will be 48 inch over G. So you have that in this case aluminum, so you have 3.9 times 10 power 3, and then we have J, polar moment of inertia. So, and this is hollow, so pi over 2. Well, let me see that. No, should be, let me check here, should be here pi over 2. This in pi over 2. So can you correct that? Pi over 2, pi over 2, pi over 2. And that is pi over 2. And that is the appendix inside back of your cover to find out the polar moment of inertia for circular cross section regardless of hollow or solid. So this is 3 outer radius, inner radius square, and that one what you have for the J, and then plus also BC, so BC 10 pi again, 2 feet, it will be 24 inches, divide by GC stainless steel, so 10.8, 3 power of 3 KSI, and then pi over 2. This is a solid, so 3 square, 3 skip, not 3/4. 3/4. Did I write 3/4 here? Yep, 3/4. 3/4. And then plus. Now, for CD, the torsion that you can see negative, so you have to keep that in the angle of twist, because the negative, it means that the twist, the angle is changed opposite to the positive based on the right hand rules. The positive, it means it same as the direction of the twist or the torque based on the right hand rule. So with that, as you can see, you have to maintain that here, positive or negative. Keep that in mind. If you add all positive, then the angle of twist is big, but that's not correct. So here, keep that in mind, negative 36, because that is 3 feet. And then we have also stainless steel, 10 power 8, power 3, 5 over 2, 3, 4, and then, and that's it. That's it. So from that, what I'm doing here, no, not 10.8, 10.8 times 10 power 3, and then 5 over 2, 3, 4, and that's what I mean. From that, plug everything, we have 5 AD, which is the angle of twist of A with respect to the fixed and D. Add all of them together. Keep in mind there is a negative in there. Don't add all magnitude. Have to consider the positive and negative. 3.35 10 power negative 3. What is the unit? What is the unit? Radian. Keep that in mind. And that's what we done for this problem. So many things you consider. Something that you confuse. First, is the I just mentioned for the 5, as you can see, the torsion positive or negative, it need to be considered in that equation. And the G, the J, the L is applied for that segment only. Depends on material for G, depends on the geometry cross section for J, depends on the length of that shaft segment for L. Keep that in mind. And it always, even the question don't ask you to draw the torque diagram, it always good to draw the torque diagram, to visualize what's going on, what is the internal torque distributed throughout the shaft. So with that, we done for worksheet 6B.